Hello friends, welcome you all to the 51st lecture on functional analysis and its applications. In this lecture, we will discuss the partial order relations, total order, maximal and minimal elements, and Zorn's lemma. These are the contents of today's lecture: partial order relations, total order, first and last elements, maximal and minimal elements, and Zorn's lemma. Partial order relation. A relation R on a set X is said to be a partial order relation if it satisfies the following three conditions. X or X for every X belonging to X, that is reflexivity. Second, X or Y and Y or X. This implies that X is equal to Y, that is antisymmetry. Third, X or Y and Y or Z. This implies that X or Z, that is transitivity for all X, Y, Z belonging to X. The only equivalence relation on a set X which is a partial order on X is the identity relation Ix, that is the relation defined by the setting X or Y if and only if X is equal to Y, where R is the relation on set X. We shall denote the partial order relation by the symbol less or equal to. This set together with the partial order relation, that is the pair X and less or equal to, is called a partial order set or poset. Two elements X and Y of a partial order set are said to be comparable if one of them is smaller than or equal to the other, that is if X less or equal to Y or Y less or equal to X. Noting point: smaller than or equal to is not used in the ordinary sense here. For example, let n be the set of natural numbers. Then the relation R defined by setting A or B, where A and B belonging to n, if and only if A divides B is a partial order relation on n. Explanation: the relation is reflexive since A is a divisor of A for every A belonging to n. It is antisymmetric since A is a divisor of B and B is a divisor of A. This implies that A is equal to B. It is transitive since A is divisor of B and B is a divisor of C. This implies that A is divisor of C. Next example, the relation less than or equal to in the set of R of all real numbers is the natural example of the partial order relation. Okay. Third, the inclusion relation proper subset on the power set Px of a set X is another example of partial order relation. Explanation: the relation is reflexive since A is proper subset of A for every A belonging to power set X. It is antisymmetric since A is proper subset of B and B is proper subset of A. This implies that A is equal to B. It is transitive since A is proper subset of B and B is proper subset of C. This implies that A is proper subset of C. Total order. A partial ordering less than or equal to on a set X is called total or linear or simple or complete ordering if either X less or equal to Y or Y less or equal to X for every pair XY belonging to X. A set with a total ordering is called a totally ordered set or a chain. Okay. In above condition, in partial order relation, here X are Y and Y are X. This implies X is equal to Y. Okay. But in total order, here either X less or equal to Y or Y less or equal to X. Okay. For example, the relation less than or equal to on the set R of all real numbers is an example of a partial ordering, which is also a total ordering on R. Hence, ordered pair R and less or equal to is a chain. For example, the inclusion relation proper subset in the power set Px of a set X is a partial order relation which is not a total order. For if A, B belonging to power set X, then it is not necessary that A is subset of B or B is subset of A. Another example, let N be the set of all natural numbers with partial order defined by A divides B, where AB belonging to N. The subset 2, 4, 8 and so on 2 to the power N of N in this case is totally ordered and hence it is a chain. First and last elements, maximal and minimal elements. Let ordered pair X and less than or equal to be a partially ordered set, that is poset. If A belonging to X be such that A less or equal to X for every X belonging to X, then we say that A is the first or the smallest element of X. Similarly, if B belonging to X be such that X less or equal to B. Okay, here A less or equal to X, here X less or equal to B. For every X belonging to X, then B is called the last or the largest element of X. For example, the set N of all natural numbers with their natural order 1, 2, 3, 4 and so on has the first element 1 but no last element. If the set N partially ordered as ... 4, 3, 2, 1, okay, then it has no first element but has the last element 1. Again the ordering 1, 3, 5 and so on 6, 4, 2. It has the first element 1 and last element is 2. Whereas ... 5, 3, 1, 2, 4, 6 and so on has neither first element nor last element. Okay. Maximal and minimal element. An element B belonging to X is called a maximal element of X if B less or equal to X. Okay, here b less or equal to x implies b equal to x, where x belonging to x. Similarly, a belonging to x is called a minimal element of x if x less or equal to a implies a equal to x. Okay, where x is the element of x. Thus, an element a belonging to x is called a minimal element of x if there is no element in x which strictly precedes a, and an element b belonging to x is a maximal element of x if there is no element in x which strictly dominates b. Here x less or equal to a, there is no element in x which strictly precedes a, and here b less or equal to x, there is no element in x which strictly dominates b. It is easy to see that if a is the first element of x, then a is minimal element in x and the only one, and if x contains a last element b, then b is maximal element and the only one. Also, a totally ordered set can contain at most one maximal and one minimal element, and these will be the first and the last elements respectively. For example, the totally ordered set A is equal to x. X lies between 0 to 1, that is 0 less than x less than 1. With ordering relation less than or equal to, has no maximal element and no minimal element. Noting that A has no first and no last element. Okay. Next example. Let C be the collection of all non-empty subsets of non-empty set X, ordered by set inclusion. The each singleton is minimal element of C. Note that C has no smallest element unless X itself is a singleton. Thus, if X is equal to set ABC, then C is equal to set of singleton set A, singleton set B, singleton set C, and set AB, set BC, set CA, and set ABC. Here each of the singletons A, B, and C is a minimal element of C, but it has no smallest element since there is no element of C which is a subset of every element of C. Also, the maximal element of C is set X, that is set A, B, C. Note that here the largest element and the maximal element are the same. Upper and lower bounds. Let A be a subset of partially ordered set X. An element A belonging to X is said to be a lower bound of A if A less or equal to X for every X belonging to A. Similarly, an element B belonging to X will be an upper bound of A if X less or equal to B for every X belonging to A. A set A may have no lower bounds are no upper bounds, or it may be have many. Okay. Zorn's lemma. If X is a partially ordered set in which totally ordered subset has an upper bound, then X has a maximal element. In this lecture, we have discussed the partial order relation, total order, first and last elements, maximal and minimal elements, and Zorn's lemma. Okay. This lecture is very useful lecture. The contents of today's lecture will be applicable in the proof of Hahn-Banach theorem. Okay. These are the references which have been used in this lecture. Functional analysis, Dover publications, written by George Beckman and Lawrence Narsey. Second, Introductory Functional Analysis with Applications, John Whaley and Sons, written by Erwin Krejcik. Third, Functional Analysis, New Age International Publishers, written by V.V. Lemieux. And fourth, Functional Analysis, Tata McGraw-Hill, written by Waterruden. Thank you.